Alright, so hi, my name is Sarah Thompson and I'm here to talk about condensation reactions. So first we're going to talk about what is a condensation reaction. And it's a reaction in which two or more reactants combine to form one large product, and this usually does result in the production of a small molecule. So in the example that we have here, we'll see two amino acids that will condense to form a dipeptide and resulting in the release of a water. And so even just from this example, we can see how important condensations are just in life and in science. So a type of condensation reaction is the Aldol condensation. And so the first step of it results in the production of an enol ion by base catalysis, which will attack a carbonyl compound, resulting in the production of a beta hydroxycarbonyl product seen there. Now there's a second step that can occur but doesn't necessarily need to, and that's a dehydration step. And so you will lose that alcohol, resulting in the production of a conjugated enone. Now this mechanism was discovered by Wirtz and Borden in 1874, so it's brand new. And the derivation of the name, the ald from aldol, comes from aldehyde because it was an aldehyde that was attacked when they were studying it, and the al comes from the alcohol on the beta carbon. I think what's important to take from this is that Wirtz named another synthesis that he discovered after himself. Rather than the Aldol condensation, he named the Wirtz synthesis after himself, and that is no longer in use because it's not very helpful. So if you ever discover anything, be very careful which one you name after yourself and make it the good one. So what we're studying today is the synthesis of dibenzyl acetone, which is the molecule seen here. It can be used in sunscreens because it has the ability to accept UV rays, which is really interesting. So obviously we can see it has a conjugated ketone there and two benzenes on either side. So the synthesis of dibenzyl acetone, the reagents that we use are benzyl aldehyde and acetone, seen there and there. It's a base catalyzed reaction, so we use sodium hydroxide as our catalyst. And the solvent is ethanol. And it produces our dibenzyl acetone by this mechanism seen here. So it's a 5-step mechanism. And the first step of that is the formation of the enolate ion. So this sodium, or this hydroxide ion, will deprotonate that carbon. And it's really important that these carbons have alpha hydrogens, because these alpha hydrogens are acidic. And so as you know, you look at this resonance, you can see that there's a negative charge on the carbon there, which usually isn't very stable, but due to resonance, this carbonyl is able to stabilize it, allowing for this enolate ion to form. And then the second step is the nucleophilic attack of the aldehyde. Now, the aldehyde, the benzaldehyde that's present in the solution, was one of our reagents, is going to be preferentially attacked rather than the ketone, because aldehydes in general are more electrophilic than acetones. And that's for two reasons. One, steric hindrance. Obviously aldehydes have a hydrogen there rather than an alkyl group as seen in ketones and the acetone that's present in our solution. And so it's just easier to attack. We don't have things in the way. The second reason is that alkyl groups, of course, are electron donating groups. And so when you have a hydrogen there rather than an alkyl group, you're going to see that it's a more electron deficient area, and there is easier to preferentially attack by a nucleophile. And so that's the reason that we'll have this product formed rather than the attack on another acetone in large quantities. And then the next step is the protonation of the oxygen, resulting in our beta hydroxycarbonyl compound, which we talked about earlier. And so that's where we are right here. And when we talked about aldol synthesis earlier, we did mention that there's a second optional step, but it's not optional in this mechanism. We need to go through and do that dehydration. So it occurs by an elimination reaction. So the alpha hydrogens are going to be deprotonated here, and that's going to result in the protonation of water As you see here, that negative charge is going to result in the addition of a hydrogen to that alcohol group, and it's going to go away as water. What's really interesting is that the conjugation of this product really increases the speed of the elimination. And you can see where that conjugation is. There's a ketone here and there's a benzene ring that's all forming this large conjugated area to increase the speed of this elimination. So now we have produced our benzyl acetone product here, but benzyl acetone, seen here larger, you can see that it also has alpha hydrogens. So it also has those acidic hydrogens that are able to be deprotonated by the hydroxide. So once it deprotonates it, much like our acetone that we saw at the beginning, it's going to attack another benzyl aldehyde, and it's going to go through the remaining 4 steps of the synthesis pathway, and it's going to produce our dibenzyl acetone product that we wanted at the end. And so that's how you get this really nice symmetric product that's really beautiful to look at, is you attack the same thing on either side with the acetone. So that is the mechanism, and